really like to spend as much time as possible doing some review, but some of that review will be in context of maybe some transport drugs, transport inhibitors. I don't know. I'm more concerned about review on Wednesday because I won't be able to have a help session for you guys. So Wednesday's sort of going to be a review session. Get you ready. All right, so that you're not freaking out. That would be a bummer. So today we're going to look at, to solve some problems, some delta G problems. And I have a bunch. I gave you some. And I was going to calculate some props, do A and B for you, but I think I'm going to let you struggle with A and B, and then C and D. So on the problem, not the current problem I gave you, but the one I gave you on Friday. Okay, that has a cell membrane on it. Okay, I think there's a part A, B, C, and D. And I'll write down their equation. Okay, so that was their equation on the problem. And the one we're using, which is, okay, this one. Okay, I gave you this one as a handout. I'll write that down underneath and we'll take a look at how are these equations exactly the same. So we use this. Okay, so instead of using the log to the base 10, most people use the natural log. And I figure it's not that hard because all you have to do is hit the button on the calculator. So that makes it easy. Okay, the other thing is, notice that here's a negative sign here, okay, not here. Okay, so this equation doesn't use a negative sign, but notice that in this equation, concentration in over concentration out, and this is concentration out over concentration in. So the inverse of this reaction of this ratio would be a positive number. Okay, so it's really the same equation. You can use either, just because I wanted, just for me, for consistency, I use this one. You can use either one. They're both exactly the same, and they give you exactly the same numbers. Okay, so what I'm going to do is I've solved A, B, C, and D already. I will make a PDF file of my solution, and I'll put it on Scholar. I'll do the same thing for the problem I just handed you today. Okay, so those are opportunities for you to work independently rather than just follow me. So today we'll cover some problems where you're just going to follow me. Is that going to be okay? Okay, and so even though the solutions will be posted on Scholar, try not to use them as a crutch. Make a really honest attempt to solve the problem before you look at the answer. Okay? So prove to yourself that, yeah, you can do it. You don't need somebody to show you how to do it. Most of this solving problems outside of the class is not so much as learning how to do it as building confidence so that you know, that you convince yourself that, yeah, I can really do it. So we're going to cover a couple problems today. One of which I have not meter. Okay. So we looked at this sodium calcium symporter, antiporter. I'm going to show it this way. Alright, so we saw this pair of proteins in cardiac muscle cells at the cell membrane, where this is out of the cell and this is inside the cell. And we notice that, oh, it's kind of cool when these two pumps are working together, is that there's no change in charge across the membrane. So if you look at the number, there's 2 positive charges pumped out, or 2 positive charges pumped in. 3 sodiums are moved in, but then they're pumped right back out by the sodium-potassium pump. Okay, so the question I wanted to ask is, do we really need 3 sodium ions to move calcium up its concentration gradient? Or are those 3 sodium ions simply there to maintain charge, no charge difference? Okay, could we get by with 2 sodium? But if we got by with 2 sodiums, then we would change the voltage across the cell membrane as these 2 pumps are working together. Okay, so we're going to calculate if this is really necessary. So I'm going to give you the concentration of calcium both inside and outside the cell. Oops. Okay. It's a huge concentration between the inside and the outside of the cell. And we're going to assume that the inside of this cell is more negative than the outside, so the voltage across the membrane will just maintain it. We'll just say minus 60 millivolts. Okay? So let's calculate the amount of energy that's going to either be required or given off as calcium moves into the cell. So we're going to set it up like we always do, just calculate the energy of inward movement, okay? And the energy of outward movement would be exactly the opposite amount of energy. Okay, so let's okay, so plug in what you know of these numbers. And I'm going to give you the value for R times T. Let's see what one I use. Every once in a while I use a different value and I don't know why. Okay, 614. Kilocalories per mole. Z in this case?
Positive 2.
Yeah, it's gonna be 2. Okay, and F, Faraday is going to be 6, I think. Oh, here's the number. Yeah, 6. Kilocalories per mole. Times 0.06 volts. This number. Okay, does that make sense? Okay, so this becomes minus 2.77 kilocalories per mole. Okay, since the moles cancel. This number, once I get it all whittled down, becomes minus 5.053 kilocalories. I probably want to look in a little bit excessive in the terms of how many significant digits. I would probably see 5.05, that's about it. But so this comes out to be minus 7.82 kilocalories per mole. Okay, so for the movement of calcium into this cell, this is how much energy is released per mole of calcium. Okay, but we're talking about pumping calcium out of the cell. Okay, so the outward movement, okay, this movement is going to require okay? So we have to come up with almost 8 kilocalories to pump a mole of calcium out of this cell. Okay, and last time, I'm just going to use Friday's calculation for sodium. Okay, so 1 sodium, I'm going back, so go back to the calculations we did on Friday. Okay, and do you find that 1 mole of sodium moving in releases 2.914 calories per mole? Is that the number we calculated? Okay, good. So is that enough to pump? Against the calcium gradient? Ooh, let's try 2. So 2 sodiums would be twice that. Is that enough to pump the calcium up its concentration gradient? No. So let's try 3 sodiums. Is that enough? Yes, so it really does take 3 sodium ions to move calcium against its concentration gradient. Okay, any questions about that? No? Okay. Okay, all right, let's do another one then. time, I'll go back and solve A and B. We can do A and B together, and then you do, of that, problem with the, that I gave you Friday. Oh, I know what we could do, and I know what we can do. Let's take a look at, and then we have two more problems. We'll take a look at the sodium glucose symporter SGLT2, okay, which, remind you, pumps glucose into the cell. Okay, with the use of one sodium ion moving down its concentration gradient. Okay, and then SGLT1 uses 2 sodium ions. Okay, but this one uses just 1. Okay, and my question is, what kind of concentration gradient? And I'm really talking about a glucose. Okay. In other words, how steep does that glucose gradient have to be before sodium can no longer power the pumping of glucose into the cell? Okay, what's the maximum gradient that sodium can pump against? Okay, so the real setup, and we're also going to assume a minus 60 millivolts. Okay, oops. So let's do just right out the real setup, because we've already calculated the energy released when sodium moves down a concentration gradient. But let's pretend we had to do it from scratch. So we're going to look at the energy of sodium moving down its concentration gradient. Okay, and I'm really going to go way more than what we need. Okay, and here's the other side of the equation. So when these two sides of the equation are equal, sodium can no longer pump glucose. Okay? So let's start out with kind of the obvious. For glucose, Z equals, what does Z equal for glucose? 0, okay? Z equals 0, so this value becomes pretty unimportant. And we don't really, I'm not really asking the question, what is the glucose concentration inside the cell and what is the glucose concentration outside the cell? What we're really solving for is the ratio. Okay? So I'm just gonna simply make, okay, so I'm just gonna say that the ratio is X. We're solving for the ratio, we couldn't care less what the actual concentration of glucose in and the glucose concentration out is going to be. Right, and we've already, in many ways, many times, and you can do it again and again and again, solve this problem. That that when you plug in the values that we've been using, we'll just say, you're gonna get this no matter. You got this last Friday, you're gonna get it again today if you solved it. RT is that, right? Okay, times the natural log of X. Okay, so I'm just going to, I'm going to bring 0.614 over the other side. Kilograms per mole over 0.614 kilocalories per mole. Okay, these guys cancel, and we end up with, my problem is a different problem. So. I got, check me, I got 4.746? Yeah, 4.75? Okay, good, let's go with 4.75. No units equals log of X, the natural log of X, whatever that ratio is, okay? So E to the 4.75 equals X.
Is it
Shouldn't that be negative?
Oh, it should be, yeah, it should be, yeah, yes. There we go, how's that look? Okay, thank you.
Is that like to the power of negative something, 4.75?
Yeah, this is negative.
I mean, when you divide that by 0.614-ish.
It's still negative,
Okay.
and it's gonna be bigger, yeah.
All right.
Got it? Okay, so now I have negative 4.75 and taking over. And I got X to equal 0 point, and it really doesn't make any difference. 0.08609. Okay, now if I take the inverse of that,
I have 6.5. Yeah,
0.0061? 865. Oh, okay, well, it doesn't make it.
It doesn't.
But you have to do that before.
Did I do this all right?
Yeah.
Yeah. Okay, so if we take the inverse of this, I got, 115. Did you guys get that? Did you do the inverse of that?
Why
Why are you inversing?
Okay, because I could say there could be a 0.000865 difference in concentration gradient, but this number makes more sense to me. There's 115-fold, could be 115-fold difference between the concentration inside and the outside. And notice I didn't specify where the concentration is high, where it's low, because solving. But what we're saying is that there can be 115 times more glucose inside the cell than outside the cell. Yeah,
But why do you inverse? Like, what's the reasoning behind it?
for the reason, what, does it say that, what's more meaningful to you? That there is the difference in concentration, the steepness of the concentration gradient is 1/.00065, or 6.
Well, I'm saying, but why inverse? Why not something else? Like, why did you choose inverse?
Because I think it's more meaningful in my head to say that there's a 115-fold difference in the concentration gradient than this difference in the concentration gradient.
I think she's asking.
Why does it mathematically, why does taking the inverse of that make it 115 fold?
Oh,
No.
it's because it's the same, I'm comparing either inside or outside or inside. I'm just looking at the steepness of the gradient, and it doesn't make any difference at this point whether the gradient is, what direction the gradient is. I'm just looking at the steepness of the gradient. And you could say, you could describe it this way, if that is a meaningful number to you. It's not to me, saying 115 times, so the difference in concentration between one side of the membrane and the other is 115-fold. And I'm not specifying direction because in this case, it doesn't matter.
Right, so
If
if
it
the
was charged, it would
0.008, is that would technically be like outside to inside?
Yeah,
Okay,
Yeah.
so really we just, okay.
I just flipped it because I find that number that have more meaning to me. Okay?
Well, it's gonna be solved inside out, or outside to inside. But,
I think in this case it's.
but it looks better if we explain
It's
outside.
just meaning, yeah, I'm not giving any direction to the steepness of the concentration gradient. I'm just measuring the steepness of the concentration gradient without giving it any particular direction. That's a lot, that's a fairly good, I don't think you will see that kind of a concentration difference. Well, maybe you will.
Is that for the glucose then?
That's
Or
for the
just-
glucose, yeah.
Okay.
Yeah. Yes, that was our question, is what does this ratio have to be? And so we're, and like I said, I don't care, in the case of a non-charged solute, it doesn't really make any difference what's in, what's out. We're measuring the steepness.
So that's the largest it can be before the pump doesn't work anymore?
Yeah, and that means that under these conditions where we used 140 something millimolar glucose out, 12 millimolar in, a minus 60 millivolts. When we use the standard conditions of the cell, the pumping of glucose comes to a halt when the difference in gradient, there's a 115-fold difference in gradient. In other words, there's a 115-fold more glucose in the cell than outside the cell. That's a lot. That's an enormous gradient. Well, we're gonna see, you're going to calculate astronomical concentration gradients in the problems that I gave you. So don't be spooked by getting huge concentration gradients, okay? These are theoretical concentration gradients, but not realistic concentration gradients. Otherwise you have kind of like syrup in the cell or outside the cell. Okay, what I wanted to think about. I think the question, there's going to be a similar type of a question in that, the first A and B in that sample set I gave you is going to be asking you how big of a concentration gradient can we get for a non-charged solute and then we were looking at calcium, I think. Okay, I wanted to think about, this is going to be an easier solution. Okay, the question might seem confusing, but the solution is going to be very simple. Okay, and this is, I'm going to give you a problem that has about the GABA receptor. GABA is a neurotransmitter in the central nervous system. It's gamma aminobutyric acid. Its receptor is a chloride channel. Okay? And the job of GABA is to open up the chloride channel. So let's think about a synapse. Okay, in a very hypothetical. Okay, here's the GABA receptor. When a neuron releases GABA, and green dots are GABA, GABA binds to a chloride channel, as the GABA receptor is a chloride channel, and the binding of GABA to the receptor opens up the chloride channel. And my question to you is, and I'll give you all the numbers you need to know, does chloride move out of the cell or does it move into the cell? And then we're going to look at, so how is that going to change the voltage of that cell with the GABA receptor? Okay, so I hope you recognize that this is a synapse. This is you can see, this is the presynaptic cell. Sending the signal to the postsynaptic cell. Okay. And we want to know, what effect does that GABA have on the postsynaptic cell? How will GABA change the voltage? Okay. So here's what you need to know. We're going to use only, and it's probably a little different from the neurons, but because we're so accustomed to using it, we're going to use the voltage at minus 60 millivolts. And my hunch is not exactly that in a neuron, but we're going to use that number.